Hello and welcome to Dr. Jim's Structures class, where we do structures by example. Thanks for tuning in.
Man's practicing fuzzy math again.
This is part 3 of a series of videos on the analysis of pin-jointed frames. The previous video showed how to analyse a pin-jointed frame using the method of joints. If you'd like to watch that video, click the link on the screen. This video introduces the analysis of pin-jointed frames using the method of sections. So, let's get to it. The frame to be analysed is the same frame that was used to introduce the method of joints. It has a knife edge support at A and a roller support at E. In other words, it's simply supported. There are point loads at joints B and C. All members of the frame lie in a single plane, the plane of the screen. So we are dealing with a plane structure. And that means there is a minimum of 3 equilibrium equations available to us. These equations are commonly expressed as horizontal forces must sum to 0, vertical forces must sum to 0, and 3 moments about any point must also sum to 0. This means we can use the principle of equilibrium to analyse substructures of the frame involving up to 3 unknown forces. This fact is exploited when using the method of sections. To get started, the reactions must be found. So draw a free body diagram bubble that cuts the beam away from its supports. The purple lines represent the cuts, and these cuts expose the unknown reactive forces. If this makes little sense to you, click the link on the screen to find out more about cuts and free body diagrams. It's one of the most important concepts in structural analysis. Next, draw a free body diagram for everything inside the bubble, remembering to include the reactive forces exposed by the cuts. Note the directions chosen for the unknown forces does not matter. The arithmetic will sort it out. By inspection, HA is minus 40 kilonewtons, and taking moments about A shows that VE is plus 60 kilonewtons. Finally, some vertical forces to show that VA is plus 40 kilonewtons. Replace the labels on the reactions with numerical values, noting that the arrow representing HA has been turned around to lose the negative sign. Next, erase the bubble and calculations to free up screen space. If you want to see a more detailed video on finding reactions, then click the link on the screen. To proceed requires a sign convention for the internal forces in the structural elements. Pin-jointed frames loaded only at their joints carry only axial forces. And here is a graphical representation of the sign convention we use. Note 1. Tensile axial forces will be regarded as positive. 2. Tensile elements are referred to as ties. 3. Compressive elements are referred to as struts. And 4. The arrows represent the forces that the members exert on the joints. Applying the method of sections works by cutting the frame to expose up to 3 unknown member forces. The term section implies using a straight line to cut the frame. That's fine, but Dr. Jim encourages you to use free body diagram bubbles to achieve the same effect. There are many sections that will expose 3 unknown internal forces. Our first section will expose the force in members AC, BC and BD. Draw a free body diagram bubble that cuts these 3 members. Now draw the free body diagram showing everything inside the bubble, including the unknown member forces exposed by the cuts. These forces are always assumed to be tensile. Note, to conserve screen space, the original free body diagram has been modified to leave only the portion of the structure inside the bubble. There are many ways to go about applying the equations of equilibrium to the free body diagram to find the unknown member forces. We will start by applying the equation of vertical equilibrium to show that FBC is plus 56.57 kilonewtons. It's positive, so the force is tensile. Next, take moments about B to show that FAC is plus 80 kilonewtons. Again, it's positive, so the force is tensile. Note B was chosen because two of the unknown forces pass through that point. FBD could be found by applying the equation of horizontal equilibrium. Alternatively, it could be found by taking moments about C. You might be thinking, we can't do that. We've already used the moment equilibrium equation. But it's perfectly valid. In effect, we're trading the equation of horizontal equilibrium for another moment equation. But be aware, we haven't created another equilibrium equation, we've simply traded one equation for another. Doing the arithmetic shows that FBD is minus 120 kilonewtons. It's negative, so the force is compressive. Record the results on the space diagram, noting that all force values are positive, because the nature of the forces is indicated by the arrows on the members. We've finished with section 1, so erase the free body diagram bubble and remove the calculations to free up screen space. To continue the analysis, we need to identify another section that will expose up to 3 unknown forces. It makes sense to expose 3 unknown forces where possible, as this will keep the number of sections to a minimum. Our second section will slice the top off the frame as indicated by this free body diagram bubble. At first glance, it looks as if the bubble will expose 4 unknown forces, but it doesn't, because section 1 found the force in member BC. Draw the free body diagram for everything inside the bubble, remembering that the unknown member forces are always assumed to be tensile. Inspection of the diagram shows that the equations of horizontal and vertical equilibrium would involve all 3 unknown forces, so for now they'll be ignored. Of course, we could apply them, and if you like solving simultaneous equations, it's the way to go. But Dr. Jim prefers to sidestep simultaneous equations when possible. So, how to proceed? Pause the playback and think about it. We see that taking moments about D will yield FAB. The downside of this is we need to know the lever arms of FAB and FBC about D. It's a sad fact of life that structural analysis often involves solving geometric equations. Fortunately, the geometry of the frame is very simple. The construction shown in green shows that both lever arms are 3.536 meters, and summing moments about D shows that FAB is minus 56.57 kilonewtons. And, as a quick reminder, the lever arm of a force, about a point, is the perpendicular distance from that point to the line of action of the force. For example, the lever arm of FAB is the distance from D to F. Similarly, the lever arm of the 56.57 kilonewton force is the distance from D to C, the same distance as from B to F on the sketch. Next, take moments about C to show that FAB is minus 84.85 kilonewtons. Vertical forces could be summed to find FCD, but that would be tedious. Taking moments about B is a better approach and shows that FCD is plus 84.85 kilonewtons. It pays to keep on your toes when doing structural analysis. Notice that we've avoided the equations of horizontal and vertical equilibrium by trading them for 2 moments equations. That's a good trade. Record the results on the space diagram, then free up screen space by erasing the free body diagram and the calculations. Now, inspection of the free body diagram for the whole structure shows that a section cutting members CE and DE will yield the remaining unknown force FCE. Note this section effectively applies the method of joints to joint E. Draw the free body diagram for joint E, then apply the equation of horizontal equilibrium to show that FCE is plus 60 kilonewtons. Record the results on the space diagram and erase the workings. Inspection of the space diagram shows that all member forces have been found, so the analysis is complete. You will have noticed that to free up screen space, the screen has been tidied up at various times during the analysis. This is fine for an educational video like this, but when solving problems on paper, all working should be retained. If you would like free, printable, annotated notes for this video, then swing by Dr. Jim's website at drjimstructures.com. A previous video analysed today's frame using LinPro, a free, lightweight frame analysis program. To watch the LinPro video, click the link on the screen. Well, thanks for watching. If you found this video useful, please give it a like and feel free to comment. Your feedback is appreciated. Bye for now. Hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.